Welcome back. In the previous video, we cover the feature importance, how to actually select the most important features in building of your model. So in this video, we are going to cover a very important topic of data pre-processing, preparing your data so that you don't get distortion in your machine learning algorithm. So as usual, we're just going to walk through the codes that we have here so that you can develop the intuition, and I'll walk through the different types of method of processing your data after we've gone through this motivational example. We import the standard libraries that we need: pandas, numpy, matplotlib, and also seaborn. And again, we are using the Boston data. And we're just going to make use of one set of data, which is the LSTAT data here, and we are storing the target data into Y itself. Now I'm just going to show you what it looks like when you do not have data pre-processing, and I'm just going to plot out the sums of squares of errors on the Y-axis and the epoch, number of repetition or number of iterations that we are doing to fit the model itself. And you can see that as we training the model, it exploded. The sums of squares of errors exploded. And that's really to highlight one key issues with the actual data itself. Let me just plot this out for you to see what the LSTAT data looks like. Now, this is what the LSTAT data look like. So I'm just plotting it out here. LSTAT is our x-axis and y is our Boston data. Notice that the non-linear relationship here, and if you actually don't pre-process the data, what would happen is that the model will actually struggle to actually fit your data, and I'll explain why in a minute. Now I just want to illustrate to you, if you just do some basic simple transformation using what we call scalar, and just basically transform the actual data itself, and I'll show you what it looks like. So this is the actual transformation itself from pre-processing library of scikit-learn. We import standard scalar. We'll revisit what standard scalar means in a minute, and basically transform both the x and transform both the y, both the x and y. And let me just plot this out, and basically we're going through the same from 0 to 100. Notice that the sums of square of error start high, around 250, and actually converge lower and lower towards the minima, or the fitting the actual model really well. Whereas this starts off with a really small number, but you can't really tell because the scale is really squashed, and it just took off as you actually continue to train. So let me just change this to, let's just say 80, and again it took off. So let me just change this to 60, see if we can actually see. Yeah, it's just having a bit of problem. Let me just change it to 0. This is let's see what it looks like. Okay, at 0 the actual sums of squares of error, basically this with 0 is basically a linear regression. There's no penalization that's being imposed here for our model fitting. Basically this code here is from the gradient descent that we used earlier in our earlier model. If you can't remember what this is, go back and have a look at the gradient descent lesson. So if you look at this, 150,000 is the sums of squares of error. So really there's actually the error rate is really high, and it's not really improving as we actually train more and more. Okay, so it's not really improving at all. Whereas after we scale it, as we train more and more, the model start to converge to the minima itself. Okay, so let's plot this out and see before transformation what it looks like, and after transformation what it looks like. This is what the standard scalar library did. It actually conformed the data to a mean of 0 and standard deviation of 1. Okay, with that, let's actually get into data pre-processing itself. There are really four main types. This is with regards to continuous nominal data, not categorical. We'll come back to categorical a little later. There are really four types of data pre-processing method that you apply to just real numbers. You can look at standardization or mean removal, min-max or scaling the feature to a range, normalization, and finally binarization. Now, the key assumptions to a lot of machine learning algorithm, these could be implicit, it could be explicit, is that the features follow a normal distribution. Normal distribution is basically with a mean and a distribution of plus and minus 3 standard deviation. Now, most methods are based on linear assumptions as well, meaning your data is linear, okay? And earlier, when you see that the data is non-linear between x and y, you got a problem. Most machine learning requires the data to be standard normal distribution as well. Now, standard normal distribution is a Gaussian with zero mean and unit variance. Unit variance basically means the variance being 1, or standard deviation being 1. Okay, so that's really a very important point here, is that if your data doesn't have a mean of 0 and standard deviation of 1, you're going to have problem converging to a reasonable solution for your machine learning algorithm. So in the scikit-learn, we often ignore the shape of the distribution itself and just transform the data to center it by removing the mean value of each feature, then scale it by dividing non-constant features by the standard deviation. So this is from the scikit-learn library, so feel free to actually have a look at the library itself, the documentation. I provided a link for you to actually have a look at. Now, many elements used in the objective function of a learning algorithm assume that all features are centered around 0 and variance of the same order. Now, variance here referring to the multiple features. So if you have 5 features, it expects all the mean is 0 and the variance are all of the same order. Same order means they are all of the same size. If a feature has a variance that is order of magnitude larger than others, meaning one could have a variance of 1, the other one could have a variance 10, the larger one will dominate, okay? And what will happen is that it will dominate the objective function and make the estimator unable to learn from other features correctly as expected. So because essentially the one with the larger variance will dominate the whole objective function altogether because of its variance. And that's in essence, this is the objective function that we looked at earlier in the gradient descent. Again, I'd just like to point you to that lecture and that video for as a refresher. Okay, so this is in essence how you actually perform a few of the different types of data preprocessing. We import from scikit-learn library the preprocessing module. And this is our so-called train. We're feeding it some basic data, 1, -1, 2, 2, 0, 0, 0, 1, 1. This is just really our sample example here. So with that in mind, so let me just go into the first one, standardization or mean removal. In this, the mean is removed. The data is now centered around 0, and this is to completely remove the bias. The bias term, if you may remember in our earlier lesson on regression, really is actually intercept. So we're shifting the whole distribution to the origin or 0, just basically removing the bias altogether so that the data is centered around 0. Now, standardization of dataset is really a common requirement for many machine learning estimator, as I mentioned before, otherwise it will behave badly. So this is really the transformation that is being done. This is the transform X, this is the individual data itself minus the actual mean itself and then divided by standard deviation. This is really transforming it into a standard normally distributed data. Now, having imported the scikit-learn input processing, the pre-processing here, we're scaling the X train. And let me just print out what the X scale looks like. The scale data pretty much is the X train transform, and this is how it looks like. So now we have -1 to 2 is the range. 1 happens to become the actual center. That's why 1 is now 0. So notice that all the data has now been transformed, and this is what it looks like. And if you actually calculate the mean, it's now 0, and the standard deviation is actually 1. Okay, coming back to this original x train here, the calculated mean with x is 0 is, if you look at this, the mean is 1, 0, 1, 2, 1 is the mean, -1, 0, 1, the mean is 0, 2, 0, -1, the mean is 0.33. Okay, so after the data is transformed, what you have now is that the mean are all 0 and the standard deviation are all 1. So keeping in mind that if you scale your training data, you must do likewise with your test data as well. Now, you are assuming that the mean and variance must be invariant between your train and test data. Now, scikit-learn makes it easier for you to, having used your training data to train your model, you use the actual so-called the mean and variance from the training data to transform the actual test data. So looking at this, this is the actual train. So the scalar itself, you instantiate the standard scalar and then you fix the X-train model. So this is the scalar now that you use to go ahead and transform your training as well as later on transform your test data. Okay, so this is how you transform your test data. The train data, if you plot it, this is what it looks like. And the actual test data, you will just use scalar to transform it before you actually run your prediction. So just revisit this concept here. Standardization really is transforming your data to a standard, normally distributed data. Okay, that's really the end of this video. In the next video, I'm gonna go and cover the other few methods. But in this lesson, because I've covered some certain intuition, it is quite extended. And also I've shown you and demonstrate to you what the standardization method looks like. I'd like you to actually try it out with some of your own data. All right, create some fictitious data and run through this exercise now, and just to actually get an intuition of what it looks like. So take a moment, and when you come back, I'll summarize this lesson. Welcome back. I hope you actually gave that a try and developed some intuition. When you come back, we're going to go into min-max or scaling features to a range. I'll see you in the next video.